In our last video on graphs, we talked a lot about how they can be useful tools for us to get information about a function or relationship between quantities very quickly. We were able to identify whether a graph is a function using the vertical line test, and we were able to see and observe and identify the domain and range of that function based on its graph. But that's not the whole story that a graph can tell. We can learn a lot more just from looking at these pictures that we have, including how a function is changing. Is it increasing, decreasing, or constant? And what are its bounds? What is its max value? What is its min value? And so that's a little bit of what we're going to explore here. Now, as you can see in our objectives, we're going to be talking about identifying intervals when these functions are increasing, decreasing, and constant. And so it's worthwhile for us to take a brief recap on interval notation. Now, loosely speaking, an interval is just like a span of values. Like maybe you start at 1 and you span all of the values all the way up to 3 and everything in between, from 2 to 1.5 to 1.375842, and all of the little numbers that fall in between there. To write this, we use either parentheses or square brackets, and we write the lower bound. So whatever the smallest value in the interval is, the smallest value in this span, comma, the upper bound, whatever the largest value in the span is. And we can do the same with square brackets as well. The difference being when we use square brackets, we're going to include the bound values, versus with the parentheses, we will exclude them. Right, so the parentheses, we are excluding the boundary values, and with the square brackets, we are including the boundary values. So for example, if we wanted to represent all of the numbers that were between 1 and 3, but didn't include the value 1 on the lower bound and the value 3 on the upper bound, we would write that with parentheses, everything from 1 to 3. If instead we used less than or equal to signs and said we want to include all of the values between 1 and 3, including those endpoints, including the lower bound of 1 and including the lower bound of 3, we would write this using a square bracket. And sometimes with these we have a certain name for them. With the parentheses, when we're not including the bounds, we'll usually call these an open interval. And when we are including the bounds and using the square brackets, we'll call it a closed interval. Now, the specifics of why we call it open and closed and what really that means are a little bit more than what we need to discuss for now. That's something we can say for a calculus course, but just knowing that they're called open and closed will help us write out our definitions a little bit nicer. And so with that discussion of interval notation, we can start to define when a function is increasing, decreasing, or constant on an interval. And so what we can say is that a function is increasing on an open interval if f of x2 is greater than f of x1 for any x2 greater than x1 within the interval. Now again, a lot of times with these more formal math definitions, they sound really fancy, but if we actually break it down, it's a little bit simpler than what it seems. So all this really means is that if we were to pick some value x1 and move to some other value that's greater than that, so moving to the right along the x-axis, and pick some other value x2, if the value of our function, so f of x1, is smaller at the further left point and larger at the further right point. And so in other words, if we look from left to right and our function values go up, it's an increasing function. So in other words, looking from left to right, if the function goes up, then it's increasing. And now, as you might expect, a function would be decreasing on an interval if it is doing exactly the opposite of that, if we look from left to right and the function's going down. Formally, we can say that a function is decreasing on an open interval if f of x2 is less than f of x1 whenever x2 is greater than x1 within our interval. And we can visualize this on a graph as well. Right? If we look at some x1 and then some x2 that's greater than it, if our function goes down from one to the other, then we would call this a decreasing function. And again, in other words here, if we look from left to right and the function goes down, that's how we know it's decreasing. So looking from left to right, if the function goes down, then it's decreasing. And lastly, we can identify a constant function by a function that doesn't change as we move from left to right. And so formally we can say a function is constant. A function is constant on an open interval if f of x2 is equal to f of x1 for any two x, so any x2 and x1 in the interval. And as you maybe can guess, if we pick some x1 and we pick some x2, the graph of a constant function would look like this, right, where those values don't change. So increasing would be represented by a function that goes up as we look from left to right. A decreasing function would be represented by a function that goes down from left to right. And a constant function is one that just stays the same. In other words, is flat or stays the same. And so let's take a look at an example here where we have a graph and we want to try to identify on what intervals is it increasing, decreasing, or constant. So if we start with increasing here, again, what we're looking for is when this goes up as we look from left to right. So the regions as we are looking this way, that the function is going up, getting higher or rising up on the y-axis. And so as we kind of follow this graph, we can see as we move from left to right here, the graph is going down and then it starts to round off. And right about here, right at 0, it starts to turn around and move up again. And all this time here, it's moving up, 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 up until we reach here. And then it starts to go down again. And then it goes down, 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 all the way the rest of the way out. Okay, and so really, this is changing direction at x is equal to 0 and x is equal to 2. And so we can see here that as we go from left to right, it's always important that we're looking from left to right here. So notice that even though this arrow is pointing upwards, that's moving right to left, and so that doesn't count in this case, right? It's always moving from left to right that we care about. But what we can see is that in this span here, as we move from left to right, our function values are going up. Right, if we pick an x value here and we intersect our function, and then we move over a little bit this way, maybe pick an x value here, this value is going to be higher than this value. And so during this span or on this interval, we can say that our function is increasing. And so let's do that here. Starting at 0 and going all the way up to 2, our function is increasing. So this would be from 0 to 2. Now, we want to be a little bit more formal with our answer than that, so we can represent this as an interval using interval notation. Our lower bound is 0, our upper bound is 2, and so we're going to say that this is going from 0 to 2. I think it's probably important now to step in as well and note that when we use a word like where or when, we're usually going to be talking about the x values. So rather than saying this is increasing from a value of 0 to a value of about 4, referring to the y-axis, when we talk about where or when, we're going to be talking about the x values. So when we use where or when, what we're looking for is what x value. And so this isn't asking for going from 0 to 4 as much as it's asking going from 0 to 2. Hopefully that helps clarify. We can also look at when this function is decreasing, right? So when it's going down as we go from left to right. And as we follow our graph, we can see that's happening in two places, right? We're going down this way as we go up to the point 0, and then we're going down this way as we go beyond the point 2. And so everything from negative infinity all the way up until 0, that's going to count. And so we can say from negative infinity to 0, but also everything from 2 to positive infinity. And so we'll need two intervals to represent this. But using interval notation, we can say this is from negative infinity to 0 and from 2 to infinity. And so on both of these intervals, our function would be decreasing. Finally, we can look at when it's constant. And in this case, there aren't any times when that would be the case, right? There are no times where our function is flat over an interval. Now you might be saying, well, Mr. G, what about this point here, right where it peaks, and this point here, right where it peaks, where it's either transitioning from increasing to decreasing or transitioning from decreasing to increasing? While I understand the instinct to say that it's flat there, we specifically defined a constant function as one that occurs over an interval, so it would have to stay flat for a certain span. And those transition points are really more of a change from increase to decrease. It doesn't necessarily have to span some interval where it's flat. And in this case, it doesn't. It's really just occurring at a point. And so we wouldn't actually call that a constant place of the function. And so for this function in particular, it's never constant. Beyond just how the function is changing though, one other piece of information that we'd like to pull from the graph is usually the max value and the min value. And it's one thing to look at a graph and identify the overall highest value and the overall lowest value, but we're also going to investigate some values that are a little bit different from that, which we call the relative max and the relative min. And they're very similar, but that relative word is going to be the key difference here. And so formally what we'll say is that a function value, f of a, is a relative maximum of our function f if there exists an open interval, containing a such that f of a is greater than f of x for all of those values x in that same interval other than the value a itself. So for all x in the interval other than a itself. And again, sometimes parsing these definitions when they're written out formally can seem kind of tricky at first, but let's see if we can break it down. Let's say we had a function that looked something like this. And let's say that this here was a. You can probably guess that this value up here is going to represent the global max, like the overall max for the whole function. But we've also got kind of a peak down here, right? And this here is going to represent our relative max. So let's think about how that works a little bit. We've got a, we've got our value f of a, and then imagine some interval surrounding this. So maybe something like this. We've got some interval that surrounds it in some kind of neighborhood of this, right? All of its neighbors of this point are smaller than it. So any value here, x, that's in this little open interval, f of x is less than f of a. And so that's what we're saying here, that this value f of a, this value up here, is bigger than all of the stuff that's around it within some open interval, so in some small little neighborhood. In other words, if it's bigger than all of its neighbors, or if it reaches a peak, you're going to find a relative max. And so alternatively, we can think of this as reaches a peak, or any point where it switches, where the function switches from increasing to decreasing, right? Because anytime that it's going up and then rounds down, everything around it is going to have to be smaller than that point. That f of a is going to be bigger than all of the f of x's around it. And now, as you might expect, defining a relative minimum is going to be almost the same. We just have to do the opposite, right? So we can even come in here and switch out relative maximum, and we'll replace that with relative minimum. And we'll say that a function value f of b is a relative minimum of f if there exists an open interval containing b such that f of b is less than f of x for all x in the interval and x is not equal to b itself. And we'll be able to see this on a graph in almost exactly the same way, except instead of when the graph reaches a peak, this time it's going to be when it reaches a valley. And so if we explored a function that looked kind of like this, we could identify this point here as a relative min, right? Because this value f of b, our relative minimum, is less than all of the values that live around it. If we were to draw some small interval here and pick any value x, this value f of x is less than f of b. And so this does really meet the definition as we've written above. Similarly to before, we can also think of this as whenever the graph reaches a valley, or kind of similar to how we described it when we said a max is switching from increasing to decreasing, a min would be from switching to decreasing to increasing. So when the graph switches from decreasing to increasing. And so at least for now, whether you think of it in terms of the formal definition or you think of it just in terms of a max being any peak and a min being any valley, or a max switching from increasing to decreasing and a min switching from decreasing to increasing, all of these ways will help you get to the same point, which is to identify a relative max or a relative min. And so let's see if we can take a look at this graph and identify those relative maxes and mins. And I'll note here too, just because of the different wording, that this is also often called a local max. So whether you see relative max or local max, it's all talking about the same thing. Within the neighborhood of that point, all of its neighbors have to be smaller for it to be a max. That's kind of like the local sense. And so let's look first for the max values. Okay, we can see our graph is going down at first from left to right, and then switching to going up. That clues us into a min. And then from going up, it's gonna switch to going down, which clues us into a max. And then from going down to going up, which clues us into a min. And so we can identify this point here as our local max, as our relative max. And so this isn't labeled with full detail, so we're just gonna estimate the value as best as we can here. This looks like perhaps it is maybe 2.5. We'll call it 2 for now, just for simplicity. But what we can say now is that this graph has a max of 2, and this occurs at x is equal to 1. Right, so again, this is sort of touching on the difference between the question what, which will usually refer to the y-axis, versus the question of when and where, which usually refers to the x-axis. So if we're talking about when it occurs, it's going to occur at x is equal to 1, right? That's right here. And the actual max value itself, like what's the actual value, that's going to be 2, which occurs right here, so along the y-axis. So the actual max value itself is going to be the y value. When does that max value occur? That's going to be the x value. And so we have a max of 2 that occurs at x is equal to 1. Now we can explore the mins. We can see here we have a valley, right? We're going from decreasing to increasing. And so we can identify this point here as a local min. That's going to occur at -2, and this looks somewhere about a value of -9. And so what we'll say is that we have a min of -9 that occurs at x is equal to -2. But we're not quite done just yet, because we also have another point where this reaches a valley. It's not as steep of a valley perhaps, but it still does go from decreasing to increasing, and that's going to occur right here. And so this value looks to be maybe a little bit less than the one we had before, so maybe we'll call that y is equal to 1, and this occurs at x is equal to 2, and so we can say we also have a min of 2, which occurs at x is equal to 2. And that's it in this case. On both ends here, these are going off to infinity, and so they're not ever going to see another local max or min. They're never changing their slope in either directions from here. And so we have a max of 2 that occurs at x equal to 1, a min of -9 that occurs at x is equal to -2, and a min of 2 that occurs at x is equal to +2. And those would represent all of our relative mins and maxes for this particular graph. Hopefully you found this helpful. I think because graphs can be so informative and so informative in such an efficient way, it's really worthwhile to investigate some of these characteristics and properties of them and develop these skills, because it really does make for a quick and efficient and powerful way to communicate about things that are quantitative in nature through using these types of visuals. If you do have any questions though, as always, don't hesitate to reach out. I'm happy to help, and I hope you have a great rest of your day.